Well, good morning, or good afternoon. This is 2:32. I'm 2 minutes late getting started on differential equations. However, I'm the only one in the room right now, so I guess we'll go on and get started, and hopefully some more students will be coming in. Where my mark is in the text, we're in Chapter 1, Introduction to Differential Equations, and 1.1 is Definitions and Terminology. So, we're at the bottom of page 9, which is example 8, particular solutions. We did the A one. What we haven't done is the B one yet. So let's try to get the B done. Here we have a two-parameter family, and this is your solution, you might say. Let me get my pen set up. All right. Y is equal to C1 e to the x plus C2 x e to the x. Okay, two-parameter system. C1 is one parameter, C2 two parameter. These can be any numbers in the world. As long as they satisfy the differential equation. And it says this two-parameter family is an explicit solution of this linear second-order differential equation. Y double prime minus 2 y prime plus y is equal to 0. And what they haven't told you is how they go from this differential equation to that solution. Later we'll be doing that. We aren't doing it yet. We're just right now, and as it says here, verify. Okay? So how do we go about verifying? Well, if this is your supposed solution, what you have to do is take a derivative and then a second derivative. So let's start with y prime would be equal to what? Derivative of e to the x is e to the x, so that would be C1 e to the x plus, now we have a product rule. C2 we can write out front, okay? And then the derivative of a product is the first times derivative of the second, so that would be x e to the x, because derivative of e to the x is e to the x, plus the second times the derivative of the first. So the derivative of the first is 1, so that would be plus C2 e to the x, okay? Now, it's perfectly okay to leave this just like that, or you could combine these two terms to be a C1 plus C2 e to the x. I don't see any real advantage of doing that, so let's just leave it like that for now, okay? You also need to get y double prime. Y double prime would then be C1 e to the x, so the derivative of e to the x is e to the x. I'm going to write the other one here, plus C2 e to the x, okay? Now we do the third one, which was our second. I'm putting it last now. Plus C2, product rule again, first times derivative of the second, x e to the x plus C2, derivative of the first times the second, which would be e to the x, okay? Now these you can combine like terms. So you have C1 e to the x plus C2, C2 e to the x plus C2 x e to the x, okay? That's what your y double prime is. So that's what we plug into y double prime. C1 e to the x plus 2 C2 e to the x plus C2 x e to the x minus twice C1. So that's going to be a C1 e to the x, and another minus 2c2 x e to the x, doesn't matter what order you do these, minus 2c2 e to the x. Then finally have plus y. Well, the y is up here. That's plus c1 e to the x plus c2 e to the x. Not x e to the x. Okay? And supposedly, all this is equal to 0, because that's what it says here. Does that jive? Okay? Well, here's a c1 e to the x, another c1 e to the x. That makes 2 of them. But here we have a minus c2 e to the x. I left off saying e to the, okay? So those add to 0. Here's a 2c2 e to the x, a minus 2c2 e to the x. Those two add to 0. Here's a c2 x e to the x, another c2 x e to the x, but here we have a minus 2 c2 x e to the x, and those add to 0. So sure enough, 0 is equal to 0. So that certainly does work. Okay? That two-parameter system satisfies that second order linear differential equation. Now, it's probably too early to be telling you this, but I will tell you since we've run into it here. If you have a second order differential equation, that almost guarantees you're going to have two parameters. Okay? And so it wasn't a coincidence that it was two parameters in second order differential equation. That's going to be the case just about every bit of the time. Okay? Now, in figure 1.1.4, which you see to the left on page 9 of where we worked that out, we've shown 7 of the double infinity of solutions in the family. The solution curves in red, green, and blue, of the particular solutions, y is equal to 5x e to the x, and that would be when C1 was 0 and C2 was 5, or y equal 3e to the x, that would be when C1 was 3 and C2 is 0, or y is equal to 5e to the x minus 2x e to the x. That's when C1 is equal to 5 and C2 is equal to minus 2. Now, I don't know what's very special about that. And I'm also trying to figure out why they show, they say 7 of the double infinity solutions in the family. The red, green, and blue are the ones they mentioned here. Red being 1 trip up, green being 1 trip up there too, and blue, can't see anything real special about them. I don't really know why they're calling double infinity solutions of the family. I can see one infinity going in each direction, and beats me why they name them that. All right. Now, these were listed under particular solutions. What they mean is for particular values of C, C1 and C2 in this case, there were 3 solutions. Okay, 3 different selections of combinations of C1 and C2. So on page 10, sometimes a differential equation possesses a solution that is not a member of a family of solutions of the equation. That is a solution that cannot be obtained by specializing any of the parameters in the family of solutions. Such an extra solution is called a singular solution. And if you go back to one we've done, I think, several times now, I'm going to clear the screen here because I don't know how much writing will follow this. Here is an equation. Y is equal to 1/16 x to the 4th. Okay? And y is equal to 0. Two solutions of the differential equation dy dx is equal to x y to the 1/2. And this is on the interval minus infinity to infinity. All real numbers. Okay? And coming up in section 2.2, which seems a long way off now, but we'll get there fairly soon, we shall demonstrate by actually solving it that the differential equation dy dx, this one here, is equal to x y to the 1/2, possesses the one parameter family of solutions, and this is a special case. Here is y is equal to 1/4 x squared plus c squared whenever c is greater than or equal to 0. Okay. All right. Okay. Now, when this c here is actually equal to the 0, then this will be 1/16 x squared, x to the 4th. And that's exactly the solution we've got there. Okay? But notice that the trivial solution, y is equal to 0, there's no c you can put in there that's going to make that a solution. Okay? As a singular solution, it is not a member of the family of this one that we just said. No way you can put a c in there and come out with y is equal to 0. No way whatsoever. Yet it is a solution to the equation. That's a singular solution. Okay? Said in the previous examples, we use x and y to denote independent and dependent variables, but you should be accustomed to seeing the working with other symbols to denote these variables. For instance, we could denote the independent variable t and dependent variable x. Okay, now sometimes this is like parametric equations. You may have called them in the past. Certainly this kind of setup. So here's example 9. I think I'll erase this and start on a clean page here since it's a new example. Now for some reason my head is clogging up. So I think since no one's in here, I'll pause just a minute and run down the hall and clear my head. Hopefully we'll be able to complete. So, all right, sorry about that. My head just started clogging up. After my last class, I noticed my phone was about losing its charge, so I went out to put it in the charger there at the main entrance, the admissions desk. And on the way back, I just picked up a piece of rock candy, hard candy that was in a bowl there by Financial Services. And I don't know if there was something in that. I usually don't like artificial sweeteners, and they don't do well by me, but I've never had them clog me up like that. I don't know if there was something in that. I don't know what it was, but I just was having difficulty breathing without, a runny nose issue. So let's move on to example 9. And I said these are like parametric equations. Here's a function. X is equal to C1 cosine 4t. Okay? Here's another one. X is equal to C2 sine 4t. Okay? Where C1 and C2 are any arbitrary constants or parameters. Okay, now here's the problem. What I was calling parameter before was the t, because I thought this was going to be an x and a y. They're not. These are, it's just that t is your independent variable, x's are your dependent variable, and your C1 and C2 are arbitrary constants, which they're calling parameters. And they say both of these are solutions for this differential equation. X double prime plus 16x is equal to 0. Okay? Now, later we'll know how they got that. Okay? Not now. They're just saying what you expect them to say, or I think they're saying verify. Okay? They're not quite saying that, but that's what they want you to do. So we need to do both of these. So let's start with the first one. Let's take a first derivative. We don't need the first derivative, except we got to have it to get the second derivative. So x prime is equal to 4c1 minus 4c1 cosine 4t, and x prime on this one is 4c2 cosine 4t. Okay? Now taking the second derivative of this first one, that'd be x double prime is equal to minus 16c1 cosine 4t, and this one would be x double prime is equal to 16 C2 sine minus 16 C2 sine 4t. Alright. Now, plugging each of those in to this differential equation, let's start with this one. Minus 16 C1 cosine 4t plus 16 times that first x, which is C1 cosine 4t. Sure enough, that's pretty obviously equal to 0. So that one works. Let's do the next one. X double prime there is minus 16 C2 sine 4t. And then add to that plus 16 times that x, which is C2 sine 4t, and that indeed also adds to 0. No big surprise. Okay? Now, they say finally it's straightforward to verify that the linear combination of solutions, or the two-parameter system, so if you take these two up here, combine them together, and you have x is equal to some C1 cosine 4t plus C2 sine 4t, and then you would take that linear combination of those two equations and take the first derivatives. It would just be the linear combination of those two. Second derivatives, the linear combination of those two. And then plug that combination into your x double prime, and then plus 14x, and you will see you, of course, get 0 again. So here's what the bottom line of that gives you, It's straightforward to verify that a linear combination of solutions or a two-parameter family is also a solution to a differential equation. And the next example shows that goodness gracious. Having a little difficulty breathing, but I think I'll get there. So the next example shows that a solution of the differential equations can be a piecewise defined function. Okay? And that's example 10. This one I'm almost certain is going to take more room than we got left, so let's clear that out of the way. One parameter family of quartic monomial functions, y is equal to c x to the fourth, is an explicit solution to the linear first order equation can't write. Whatever it is that's bothering me now makes it feel like I've almost got sick on my stomach. Explicit. Okay, that's pretty ugly. Explicit solution of the first order linear equation xy prime plus 4y is equal to 0. Okay. On the interval minus infinity to infinity. Everywhere, all real numbers. Okay? It says to verify this. So let's proceed to do so. Y prime is equal to 4c x cubed. Put that in here, you got x times 4c x cubed plus plus 4c x fourth. The question is that equal to 0? Well, good to see you. All right, we finally got a student here. Okay. Before I pick up on where I've been treading here, I either ate something that I'm not been feeling very well this afternoon, so hopefully it'll pass, but it's pretty rugged right now. I think I announced to you before, college transfer days here will be Wednesday, February 12th. That's, I think, 3 Wednesdays from day after tomorrow, or 2 Wednesdays from day after tomorrow. Okay? And that'll be 9:30 to 11:30 on the Birmingham West Campus, the academic building, which is B Hall. Okay? And then on Thursday, February the 13th, which is 2 weeks from this coming Thursday, on this campus, 9:30 to 11:30. They say in the campus cafeteria in this building, not really, okay? I don't think. I think it's in the faculty staff dining room on this in this building, which is just next to the cafeteria, because that would be the end of breakfast and the beginning of lunch. I really don't think they want this many tables set up there with people and no one have room to eat. So anyway, I think that's where it's going to be, but you'll find out, I'm sure, as it gets sooner. And then I think I told you about this from the POETS, Power Optimization of Electrothermal Systems. They are looking to recruit minority engineering students to work at either University of Illinois, University of Arkansas, or Howard University. 10-week internship that exposes undergraduate students to academic research in the fields of mechanical, electrical, and materials engineering. You're paid to get this fantastic learning experience, $5,000 stipend. $500 a week for 10 weeks. I don't know how they pay you, but maybe all at the end. I don't know. But you receive free housing, which usually includes food and free airfare there and back once. Okay? Then there's all sorts of weekly professional development webinars and other things that you'll be able to participate in. And I got to thinking this morning, I said it to my first class, you might say, why are they doing this? This is a tremendous deal. They are hungry. We, the U.S., is hungry for engineers. We're having to import engineers now from India, from China. We just can't keep up with demand because we've got so much going on, and so many people are not willing to put forth the effort to become an engineer. I mean, it's a pretty rugged curriculum, but if you do it, the jobs are waiting. You know, this indicates that they're really going to put out the money to try to get it. Now, maybe enough about that. The application deadline for this program is February 15th, which is a couple of weeks from Friday this week. Seems like it. I've got more information, 2 pages of page and a half of information here, and then a brochure with another trifold situation there. So feel free to take a look at it and apply. Okay, if that's at all of any interest to you. All right, I just finished doing example 9 on page 10. This is chapter 1, Introduction to Differential Equations, and 1.1 with definition and terminology. And the last example in this section is example 10, bottom of page 10. And this is a piecewise defined solution. What we had that y is equal to c x to the fourth is an explicit solution of this differential equation xy prime plus 4y equals 0, anywhere on the interval of all real numbers, okay? And what we did to determine if that was true, we took the derivative. Y prime is equal to 4c x cubed. Plug that into this is the verification process, back into the original equation. The original equation had an x first, and then y prime, which is 4c x cubed, so I put the 4c out front, times the x from here, x cubed, plus 4 times c to the fourth. So that's what I've got here. C x to the fourth. So 4 times c x to the fourth, that would be 4c x to the fourth. Is that equal to 0? Well, it's pretty easy to see. It is. This is 4c, and x times x cubed is x to the fourth, plus 4c. Oh, wait a minute. Have I dropped the sign here? Yes, I did. Sorry about that. That's a minus sign there, a minus sign there, and a minus sign here. Yes, because this was not working out. 4c x to the fourth, and that, of course, is equal to 0. That does check. We did verify that's a solution. Everywhere on the interval. Okay. Now, depending on what choice you choose for c, okay, if you choose c is equal to plus 1, then that equation, y is equal to c x to the fourth, is this blue curve here. That's exactly what a quartic equation looks like. C is equal to 1. If c were minus 1, you just flip it across the x-axis, and there's c is equal to minus 1. Okay? Now, you could combine these two in a weird way to be a piecewise defined function. Let's take the pink curve from the lower. That would be minus x to the fourth, because c is equal to minus 1. That would be minus x to the fourth, And then the second half, c is equal to plus x to the fourth. So here would be another solution, piecewise defined function, y is equal to minus x to the fourth for x is less than 0, and positive x to the fourth for x is greater than 0. Now one of those should have an equal sign under it. It doesn't matter which, one of them should, because you do have a value of 0. It's also a solution curve, but cannot be obtained from the family c x to the fourth by a single choice. Is c. Okay? So we'll let that lie. Now, the next thing they talk about is systems of differential equations. They don't do any examples with this, they just talk about it some. Up to this point, we have been, there we go, clogging up again. Been discussing single differential equations containing one unknown function. But often in theory, as well as in many applications, we must deal with systems of differential equations. A system of ordinary differential equation is two or more equations involving the derivatives of two or more unknown functions of a single independent variable. I'm sorry. I've got so much drainage, it's hard to swallow. Okay. So a system of ordinary differential equations, two or more equations involving the derivatives of two or more unknown functions of a single independent variable. So here's a couple of examples. This is, they number it as example 10, or equations 10. I think I will delete this, so you won't think they're related that much. Here's a differential equation. dx dt, where x is the dependent variable, t is the independent variable, is some function f of t, x, and y. Okay? And dy dt is equal to, my nose is itching and everything now, some other function g of t, x, and y. Now these don't have to be anywhere similar to each other. A solution of a system such as that is a pair of differential functions. The solution is okay. So the solution of a system such as this is a pair of differential equations a pair of differential, I guess not equations, but functions. The D still stands for differential, but these are functions. And they name them x is equal to phi of t, and y, phi 1 of t, and y is equal to phi 2 of t. Defined on the common interval I, each that satisfy the system of equations. All right, that didn't say much. They didn't give any clarifying part. Now, the remarks I tend to want to skip through, but I do want to hit this. We'll see in some of the chapters that follows there are some more nomenclatures here. We'll see in the chapters that follow a solution of goodness, I can't talk. A solution of the differential equation may involve an integral defined function. It seems like that's not much of a solution if it's given in an integral, but sometimes that's all you can do. If that g that's in that integral is not integrable, you got to leave it in that form. Okay? Now, if you take a derivative of that, you're going to get g of x out of that. And the integral that's often said to me is that integral that you can't take the integral of. You just have to leave it in integral form. That's often called non-elementary. That is, an integral of function g that does not have an elementary function antiderivative. Now, what do we mean by elementary functions? These are non-elementary. What are the elementary? Well, all constant functions are elementary. Polynomial functions, always elementary. Rational functions generally are elementary. Exponential functions always are elementary. Logarithmic functions within domains are elementary functions. Trigonometric functions at sine, cosine, tangent, cotangent, secant, cosecant, all elementary functions. And the inverse trigonometric functions are elementary functions. Okay, I'm not going to say any more about it now. Now, they've been naming several different types of solutions. You have trivial solutions, you have singular solutions, we had particular solutions, and imparameter families of solutions, okay? When you put maybe not all those together, but many of those together, then is what we call the general solution. Okay. And we'll be doing that more directly in subsequent chapters. So that finally finishes 1.1. As we said before, the homework exercises are any of the odds 1 through 7 whose answers are in the back. Number 9 if its answers are in the back, and they should be. 11 and or 13 if those answers are in the back. 15 and or 17 if those answers are in the back, and they should be. 19 should be in the back. 21 and or 23 should be in the back. 25 and 27. Those should be in the back. Okay. Can't tell if 29 should be with 25 and 27 or not. I'd say do it separately. 31 and or 33, if those are in the back. 35 if it's in the back. 37 and 49. And 41 is the last one. Okay. The discussion problems generally are not in the back, so if you do find some that are, you can work through those, but usually they are not. However, not a bad idea to look at some of them, because some of them may have some potential paper topic implications. For instance, number 51 is talking about the folia of Descartes. You can either write about Descartes or what this folio was, how he found it, how he messed with it, dealt with it, and if it has any practical applications. That's just one thing I saw because it sort of was bold and it reached out and grabbed my attention. So that finishes 1.1. Let's go to 1.2. I don't know what's going on with my head. Earlier, I was having so much drainage, I had to break and go down and clear my head. Now I feel like my head's so dried out. My throat's dry, everything's dry. I don't know if there was something in that piece of candy I ate or what, but I'm not feeling well. All right, 1.2 is dealing with what we call initial value problems. All right. Now they're going to start with the big, hairy, all, of course, inclusive definition, and later we'll work with ones that are a little bit more reasonable. Okay? So here's what we've got. Got a differential equation to solve. Now this is written in, I can't remember what form they called this, the general form or something like that. That you have the nth derivative of some function y with respect to some other function x. I'm sorry, nth derivative. And this is some function of, now let's imagine what it could be. Certainly the independent variable x certainly can be that. It can also be a function of the function y, the first derivative of y, and on and on and on up to and including the n minus first derivative of y. Okay. Now that's very symbolic, not very, in my mind, instructive, but basically what it's saying, if you have some function y, and it's a function of the independent variable x, y is the dependent variable, and you have the nth degree, the nth derivative of that. Nth derivative, by manipulating and adjusting things, can be written as some function of x, that's the independent variable, y, the dependent variable, and all the derivatives of that dependent variable up to and including the n minus first derivative, but that's as far as you go. Now, take a look at this. How many variables do you have here? 1, 2, 3. Now notice this is the third variable, but it's just the first derivative. So the n minus first derivative would be, okay, add 2 to the number of derivatives here, and you got which variable it is. First derivative, that's the third variable. This is the n minus first derivative. Add 2 to that, you get n plus 2 variables. 1, 2, 3, 4, 5, up to n plus 2 variables. All right. And you have an nth derivative that involves those two. So you may think of the x and the y as being the other two that you're dealing with there. All right. Now, if you have that, okay, now notice, n plus 2 variables, okay, these can be subject to, and we'll talk about what this means later, and what we're subject to are a set of conditions. These are what we call initial value conditions. Okay, now a little bit about that. Y of x sub 0 is equal to y0. Okay, now there's a little bit of me that sort of takes exception to the title, initial value problems, because it's not necessarily the initial value the function can take off. It's just any unique value, okay? So the value we're going to use is x sub 0, okay? And y is going to be evaluated there, and that'll give you a value y sub 0. But you're also going to evaluate y prime at x sub 0, and that will be y prime of 0, okay? I'm sorry, of x sub 0. Right. This is coming out so ugly. Let me fix it. That will be y prime sub 0, okay? No, sorry. Sorry about that. y1, okay? That had a y0, this will be a y1. These are just values. No reason to mix up the, what you're calling them here, okay? Then we'll also have y double prime at x0. That will have some value y2. Y triple prime at x0 will have some value y sub 3, okay? And we'll keep on going here, dot, 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 up to and including to y to the n minus 1, the n minus first derivative of y at this particular value x sub 0, and that will be equal to, now again, notice your primes here, y prime, y1, y double prime, y2, y triple, y prime. So this will be y sub n minus 1, okay? Now, those are the conditions, okay? Notice how many of them you have. 1, 2, 3, 4, 5, 6, 7, 8, up to n conditions. So nth derivative of the function, you have to have n initial conditions, okay? But again, remember, initial doesn't mean first value, just some value, but notice every function, every derivative of the function is evaluated at that same location, at that same initial value or common value, okay? And but each one of those gives you just some variable, value, okay, not variable, value, okay? Now, and if you will, please keep up with time. I don't have a watch on me. I've had to take a break or two, so I've lost all track of how much time we spent. So, what's that? 20 minutes, okay. Thought we had plenty, but I just didn't know how much. All right, now, these y's here, y0, y1, 2, 3, 4, up to y sub n minus 1, n of them, okay, you might say 1, 2, 3, 4, 5, 6, n minus 1, and this would be n, okay, so there's n of those values. Because you got an nth order differential equation, you've got to have n of them. Those are arbitrary constants, okay? And this is called an nth order initial value problem. Now, we'll call this IVP, initial value problem, okay? The values of y of x and its first n minus 1 derivatives at x0, all at the same point, are those values we said, x0, x1, okay. Those are called these individual things here, okay, all those, and the dot, dot, dots too, these are called your initial conditions. You have to have one for every degree of your derivative, every order of your derivative, and these initial conditions are often abbreviated IC, capital I, capital C. Those are your initial conditions. So, how do we go about solving an if order initial value problem, such as that one that I have there? It frequently entails first finding an n-parameter family of solutions of differential equation, and then using the initial conditions at x equals 0 to determine the n constants in the family. Okay? The resulting particular solution is defined on some interval I containing the number x of 0. So, this is kind of a geometric interpretation. We got n equal 1, meaning a first order differential equation. Okay? N equal 2 will be a second order differential equation. So the first order one, I think I'll go to a clean page here because this may take just a little bit of space. Here's the first order. dy dx is equal to f of, now remember, always your independent variable will be there and your dependent variable. And then if you had any higher orders on the left, you do 1 minus that on the right. Well, this one, that's first order differential equation, so you only go to the 0th order of y, which is 1. Okay? Now, and how many variables you got? One more than what you have ordered there. I think I may have said 2 more over before, but it's one more. Okay? So, how many initial conditions do we need? First order differential equation, 1 initial value. That would be y at x0, whatever that x happens to be you know something about, that's all you've got. Okay? And that would be some y value. Okay. You don't need to know any first derivatives, second derivatives, anything else, just that 1 initial condition. All right. Now, here is the geometric interpretation of that. You have a series of solutions for this differential equation. They're just drawn in there. But you do know that at x equals 0, at x sub 0, the value here is y sub 0. So that one's out, that one's out, this one's out, that one's out. This is the only one that gives you that value. So this you know is your solution. The others may have solved the equation, but they didn't match the initial condition. So your initial condition pins down, fixes it. Okay? Now, this next example they give, I think, leaves a little something to be desired, but let's do it. The second one is a second order differential equation. Okay? And this is equal to farm as a function of certainly the x, certainly the y, but because this is a second derivative, we'll have a y prime here. Okay? So again, the order of the differential equation, you'll have one more variable in there that it's a function of. Okay? Then, how many initial conditions will you have? 2, because it's second order. Y of x0, we just arbitrarily use that as the value, is equal to y0, but then y prime at x0 is going to equal y1. Okay. Yeah. So that's how they set these up. Now, what does that mean exactly? Well, here's a value for this function at that value. There's a fixed value there, just like it was over here. But now we have the additional condition that the slope, that's what your first derivative tells you, the slope at that point is some fixed value as well. So not only do we know the value here, we know the slope here. Here we didn't need anything, just the value. One piece of information over the first order. Here we need two. Okay? Now, this is what leaves me a little less than pleased with this. They show a variety of solutions of the differential equation, but they pick a point at 0 and find that y0, and it looks like that would do it for you. Okay? What they really should have shown here was several different functions passing through that one point. At least two, and showing that one of them has this slope, one of them has some other slope. We're only interested in the one that has this slope. So that would be that. The way they've drawn it here and talked about it, it seems like a single initial condition would have told you that you didn't need the second condition. But if you had a second curve that was going through that same point, now that first derivative distinguishes which one you do. Okay, that's a sort of a picky little point, but it is it just seems like it would be a little more general if they had included that. Now, I've been complaining they call it initial condition when it isn't necessarily the first value you could use. What they say, the words initial conditions derive from the physical system where the independent variable is time t and where y of t0 is y0. And what they're implying there is t0 equals 0. Well, it doesn't have to. It could be some other time. So anyway, trying to think of a good example of this. I'm not coming up with one now, so let's just look at example 1. And this goes back to exercise 1.1, problem 45, which I don't think was one of the ones that we did, because that was one of the discussion groups. It said you were asked to deduce that y is equal to c e to the x is a one-parameter family of solutions of the simple first-order differential equation y prime is equal to y. Okay? And all the solutions to this family are defined on some interval negative infinity to infinity. Now, if we impose, so here's what we've got. Let me start over with a clean page here. All right. Here we have a y. We have a y is equal to c e to the x. Okay. Say, before they were asking you to deduce that, that's a one-parameter family of solutions for this simple first-order differential equation, y prime is equal to y. Okay. Now, we know the only function whose derivative is itself is the exponential function. So, no surprise, that's what it's going to turn out to be. Except we have that arbitrary constant c. Because it's a one first derivative, you need at least one arbitrary constant. So you have an infinite number of solutions that will all work. Any value for c you put in there, still going to work down here. Okay? So, there is that. All the solutions in this family are defined on the interval minus infinity and infinity. So what if we impose an initial condition? And here's what they're suggesting. Y at some initial value. Now it sort of makes sense to call it 0. Y of 0 is equal to, say, 3. Yeah, there it is. I lost it on the page there. Okay, so what we're going to do, anytime you have x equals 0, plug in y is equal to 3. Where's your solution? So this tells us that 3, that's your y value, is equal to c, that's your arbitrary constant, e to the x is 0. Okay, well, what's e to the 0? 1, exactly. So this tells us that c is equal to 3. So now we can go back and say y is equal to 3 e to the x. And that will work for every well, I mean, whatever you want to call it. You know, this will be the one that fits that initial condition. None of the others will. Infinite number of solutions, but that's the only one that will satisfy that initial condition. Okay? Now, so here was your equation. There was your initial condition here. Differential equation, initial condition, and plug in, there you get it. Now, what if we demand that the solution curve pass through a different point, like 1, 0? Then your initial condition would be y of 1, 1, negative 2, is equal to negative 2. Okay? Well, we go back to our initial problem here, and you have the y value here is negative 2. It's equal to c. Now, it's not the same c. It won't be the same c. E to the 1. The x value is 1. Well, what c does that give us? Goodness gracious. Okay. C would then be equal to minus 2 over e. Now remember, e is just a number. We treat it like a function sometimes, and it is, but it's just a number. It's an exponential function of the base e, okay? E is just a number. And this is like 2.7, blah, 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 blah. So this is something a little bit greater than, or less than negative 2/3, okay? Now, all right. Now, here's how geometrically those two pan out. The top one is this one. When x is equal to 0, y is equal to 3, it must be this curve here. These curves they show here are various curves. The blue curves are when c's are positive. The pink curves or red curves are when c's are negative. Okay, the value for c is negative. This is the first one. What was that answer? There it is. There it is. Y is equal to 3c to the x. When x equals 0, y is equal to 3 because that. X equals 0, e to the 0 is 1. Okay? So that would be the blue one up there. If you want this one that has this point here on it, 1, negative 2, it's got to be a negative value. So this c is going to have to be negative to fit the pink bound here, and that would give you this, that C value is, and I don't have a calculator, so I can't give you even an approximate value, but minus 2 over E would be something on the left, I believe, of negative 2/3. Okay. The next example illustrates first order differential initial value problem. And this, notice how the interval I, definition of the solution, y of x, depends on the well, I don't know if you remember before, anytime you have a differential equation, it comes with an interval associated with it, okay? And this is one that definitely is interval dependent, okay? And you'll see that this is as good an example of this as I think you'll see. All right. It says in problem 6, a chapter from now, okay, you'll be asked to show that a one-parameter family of solutions of the first order differential equation. Let me go to a clean page here. Here's your differential equation. Y prime, first order differential equation, plus 2xy squared is equal to 0. Now, one thing different from this one, some of the earlier ones we were doing, this one's not linear. Nothing requires it to be linear. This is not a linear differential equation. Why? That y is squared. And for a linear differential equation, your derivatives and your function y can only be raised to the first power. Okay? X's can be whatever you want them to be, but the y's can only be the first power. And there's no way to rearrange this to make it linear. So this is a nonlinear. Well, here's a solution for it. There's a differential equation. Here's the solution. Y is equal to 1 over x squared plus c. And that solution there obviously is a nonlinear solution as well. Okay? Now, what if you impose this initial condition? Y of 0 is equal to negative 1. Okay, y of 0 is equal to negative 1, I think it is. Okay. All right. Now, we do with this, plug it into our solution. The y is negative 1. Is equal to 1 over x squared x squared, because the c, I put 0 in the wrong place. Okay. All right. X equals 0, 1 over c. Okay. So that means, that implies the c I'm going to multiply both sides by c. Minus c is equal to 1. C is equal to minus 1. Right? I think so. Okay. What's that? Oh, we're out of time, sorry. Okay, let's just see. Yeah, C is -1. That's what we've got. Now what we're going to do, starting next time, is hit that first bullet there, right under example 2, and we'll look at the 3 conditions, considerations they have here. We'll go from there now. This was a very short section. I think you can do number 1 if that answer's in the back. I think you can do 3 or 5 if those answers are in the back. I don't think let's stop there because the rest of them are second order, and I think we're going to hit that with example 3. So we'll pick up and go from there. Okay. Any questions? I forgot to turn the light on for you there now that it's getting cloudy. I noticed that.